And the first presentation will be made by Mr. Andrey Sechin, the scientific director of the company Racurs. He will speak about the photogrammetry and parallel computing software and hardware. Hello once again. My today's presentation will be a continuation of one of the presentations at the previous conference, where I told visitors about my vision and trends of how digital photogrammetry is to develop, including digital photogrammetric systems. One of such trends that I considered as such was the ever-growing use of parallel computing for more rapid results. And Yuri Reisman mentioned server systems that they use to supply their software. That's what I'm going to talk about now. Where it comes from? Actually, basically it's based on the ever-growing productivity of image acquisition systems. Like 2 Pleiad satellites can capture up to 2 million square kilometers, 2 million square kilometers per day of ultra-high resolution, or Vision Map can acquire up to 5,000 square meters with 20 centimeter pixel resolution. And the oblique image is also growing. Instead of 1 image, 5 images are acquired simultaneously. So we're talking about huge exponential growth of raster data, and the data which need to be processed. And to process it quickly, you need good computing power, because some people do not realize why their computing takes 5 days sometimes. I will speak mostly now about top systems. I will speak about parallel computing. At the same time, I'm not going to touch upon such things as GPO as an integrated core or inter-Xeon. I will speak about cluster systems, and partially what I will tell you about are also server-based systems that Yuri mentioned in his presentation. This is a computer cluster which includes 200 computer cores that can be bought for less than $100,000. I think it is quite affordable for a good, sizable company. I'm not going to look at all algorithms which are used in photogrammetry. I will speak about the simplest things. That is how to build orthophoto mosaics. And I start with a assumption that I already have a rectified block, and I just need to build mosaic split into trapezes and stock sheets. And the procedure of building such mosaic, why I chose this algorithm, because this is, I think, the simplest thing which photogrammetric processes have. And I will speak a bit about some of the hidden tricks that processors can trip over during the data processing. First stage is when I put this data into the system. Second stage, well, there could be other ways of building this algorithm. Anyway, second stage, for each of the input images, I use Orthophoto for it. Then these images are put together, and I need to calculate the cutoff lines. Well, I will have the final result from one image and the other. Then it would be good to have a beautiful image so that I wouldn't see these cutoff lines on the mosaic. And for that, I need to rectify the brightness. And finally, I will have to put it all together into a single mosaics, split into stock sheets. I will briefly speak about all these stages. Word tile was used today repeatedly, and the word tile usually means when we split input rasters. Like, for instance, if you have a huge satellite image, then it can be supplied in form of a set of separate images, which are called tiles, and some additional file which tells how to put these images together. But very often it is more convenient to use these tiles within such tiles. This comes from the documents of either Spot or Pleiad satellite. This is an internal structure of the file, which should also build out of tiles, which simplifies the processing and visualization. And for instance, to make sure that the photogrammetric system visualizes these images quicker, it's better to store these tiles in different resolution aside from the source images. We could have compressed images as well. Also, transformation of each image is trivial. We take our cores, our processors, and at the entry point of each GPU, if those were satellite images, we also divide them into tiles of this space or satellite images, and each process implies processing of this, and all computer systems, all GPUs are going to be loaded up. Then I have to build the cutoff lines. Here I start having first problems. The simplest thing I need to do is to take nadir part of each image with the least distortion, and for that I need to use the Baranov diagram. This is a very simple geometric task, but unfortunately it cannot be done by many processors. And then I can already align these cutoff lines so that they do not cross roads on the right angle. And using the Baranov diagram, I can specify or make them more accurate. This is much easier thing. I can take each cutoff line of this Baranov diagram, send it to the processor input section, and each one of them is then rectified like that. Then it would be good to have a more homogeneous results so that it doesn't show these cutoffs. Again, here, this task can be performed in 2 stages. First, I don't want to see the cutoff lines. For that, I need to compare the archetypes of these different images and remove these cutoff lines. And for that, I can distribute it among different cores of the computer, compare these images, and build and rectify the brightness here. But if one of the section of mosaics has dark images, others have light images, then I will have to do global rectification of brightness, and this, again, cannot be done on parallel by different cores. And the final stage is to build the resultant image when I know the function of brightness rectification, when I have orthophotos, when I have cutoff lines, when I know which image goes where. And as long as I have my input images were quite big and they were quite numerous, then the final result will be huge, but it is not stored in a single file. It is split into trapezes or pieces or some standard sections. And then I split it into different stock sheets, and each processor is working on its own stock sheet, and that's how I can do it much faster. That's what I was talking about in the beginning. In any algorithm, whatever it is, there is a part which can be done on the parallel and the part which cannot be done on the parallel. T1 is the time which is required for one processor. Alpha by T1 is something that I cannot do faster. and all the rest means that the more processors I have, the faster it will be. So for Mosaic Building, 10 minutes is spent on the tasks which first I do the text that take 10 minutes, for instance, and it doesn't matter whether I have 1 million processors, still it wouldn't take less than 10 minutes. Here we have a typical task of building mosaics for aerial photography or satellite photography. Some of the processes which cannot be performed on the parallel, which I mentioned previously, but there are others, of course. It takes usually about 1% of the time. And if I take 100 computer cores, then in fact I can increase the speed almost by 100 times. And I will show you some of the examples. First example is the satellite imagery. We used a cluster with 100 cores with the overall area of about 20 images of resource P. It was 21,000 square kilometers. The area of Mosaic was bigger because the block had a different difficult form, and there were sections without a single image. And in this cluster, it took us to build it 50 minutes. If I had a single core computer, I would have to wait 2 days to see the final results. The second example, this is UltraCam Eagle. Again, we used 100 CPU core with only 510 images, a mountainous area, size of ground pixel size was differed from 3 to 5 centimeters, and it took us 101 minutes to calculate this cluster. If I didn't have the CPU cluster, it would take 4 days instead. But when I was talking about this, I forgot to mention one important thing.
Not only am I not able to unparallelize brightness and other features, I have an operation to exchange hard drives. Before I can read or record on hard drives, I will not be able to solve my task. So mosaic generation task is simple. I have to be consecutive in reading my images and recording them. In my company, we have been using good professional RAID controllers, ZTFS file system on Linux, and that gave us about 300 megabytes per second. As for some other photogrammetric tasks, we ran into challenges there. I have 100 cores, and my file system is fully loaded. It's being used to read or to write on hard drives at all times. So we started to sort these things out, and the process that we launched required random access, not consecutive. This is a storage system. This storage system did not provide us with a chance to use it fully. And the only way to make hard drive exchange operations faster is to use parallel systems. I mentioned RAID system. RAID is in fact a parallel data storage system. I will not elaborate on RAIDs. One of them is called striping, and the other one is called mirroring. Imagine that you need to record some data on a hard drive, and the hard disk fails. Then I used 2 hard drives. So one portion of my data is recorded on one hard drive and the other on the other hard drive. But if I need to read this data, no one can warrant that I will be able to read simultaneously in parallel from 2 hard disks. And this is where mirroring coming to play. If I have 5 hard drives that recorded the same data, then I can read it 5 times faster from these hard drives. So we set up an experiment. We included 5 hard drives in one system. We use Oracle system with quasi-container. So when we used 5 mirror hard drives, I lose my capacity 5 times. But we did manage to increase the speed 5 times. So that brought the time spent from 120 minutes to 30 minutes. I think you heard that now mostly solid-state drives are used that operate as a thumb drive. So a hard drive has to wait for the head to reach the right place and read the information. And as for flash drive, you can read any data from any part of the storage area. So what I did is I increased the speed 3 times more. But in my case, the storage system is separated from the computing cluster. So I needed 2 times faster networks. So even if I take more than one solid-state disks, solid-state drives, I will increase performance by several times, but the speed of connection or speed of network will start failing me. The more cores you have, the faster they operate. The more intensive the exchange of information between hard drives and the system are necessary. Last year, DDR4 standard was released. I think we can expect DDR5, and I hope we won't hit any snags there. Thank you very much. That's all I wanted to tell you. Thank you very much. This is a very topical subject. We're all in the same playing field. We are going through that earlier or later at various time points. Are there any questions? The microphone is not operating properly. I think what you mean are new digital elevation model algorithms. Should I repeat my question? No need to repeat. Do you use algorithms from computer vision, and if yes, when do you use it in photo mode? There is a special library which I think Matthias mentioned today, Open Vision. I'm sorry. the algorithm mentioned there is not suited for us. It's not working for us. We have to write it ourselves. Also, there is a process of triangulation, right? Any ideas on how triangulation can be parallelized? It's already parallelized? We are working on it. We divide blocks into sub-blocks and then we adjust them. Indeed, it's parallelized and together with the solver, it's working. No further questions. Thank you very much.